Very good morning, students. The topic for today's lecture is choppers and inverters. We know that advancement in semiconductor technology has brought revolution, and as far as control is concerned, the industrial applications are concerned, and with advancement in this, we also have requirement for variable supply for our machinery. So, choppers and inverters play a very important role in that matter. Chopper is a static device. It is made up of certain components in which thyristor is the main component. It can be any other device, switching device like MOSFET, triac, etc. The purpose of chopper is to convert a variable DC supply from a constant DC supply. So, it is basically converting a fixed DC into a variable DC supply. That is why it is also known as DC to DC converter, because we are converting a fixed DC into a variable DC, and it is required for various applications like motor control, because we want to operate machine, particularly your DC motors, at variable speed, and we know that if we want to control the speed, voltage control is there. So, how to vary that? It is varied with the help of this chopper circuit, and there are many other applications like traction, then Marienhurst, etc. So, where the choppers they are being used. So, mainly choppers are very effective as far as the drives in machines are concerned, and we can also call this as DC equivalent of AC transformer. What we do in AC transformer is that we get different voltage level using transformer. So, here also we are getting different voltage level of DC, because transformer action in DC is not possible. So, how to get a variable DC supply? So, it is possible with the help of this chopper device that we can get that variable DC supply. And thyristor converter, I told you that thyristor is the main device. I hope you know about a thyristor is switching device. So, it has brought a greater efficiency. Why? Because it is working on a single pulse. It has very fast response, lower maintenance, and it is small and smooth control. The earlier control that used to be there, it was using adding the resistance in the circuit, so which was causing certain losses or friction losses also, and it was requiring higher maintenance. But as far as thyristor control is concerned, we simply need to apply a pulse, and it is going to control that voltage. That is why it is giving you very high efficiency and very fast response as well. Now, this is the circuit for chopper. If you see this particular, this chopper is acting just like a switch, and switch, it is made up of certain switching device, just like your thyristor. It can be your MOSFET, it can be your transistor, and if you this is represented by this box, it represents that it is not only a switch, but there are also commutative circuits. It means it is having that option to apply a pulse, to turn it on, and to commutate it by force commutation. So, that whenever we require to turn it on, we can turn it on, and when we want to close it, we can turn it off. And see this switch, we are having a inductor and a load connected to this. This is the typical diagram of a chopper circuit, and we are having this freewheeling diode connected in parallel to the load. Now, how does it work? Whenever we turn on this switch, we close this switch, what happens? This voltage, it is applied across your load. Freewheeling diode is reverse bias, so it will not conduct. So, on the whole voltage that is here, that is applied across this inductor and across your load. So, we can see here that whenever it is turned on, we can get the voltage, this particular waveform you can see here, and when this switch is opened, there is no this supply, it get disconnected from here. So, no voltage appears across your load. So, we can see that during turn off time there is no voltage here. Again we can turn it on, and then this voltage will appear, then we can turn it off, and we will not get any voltage across the load. So, the voltage across the load will appear only when the current flows through this. So, what it is doing is that we are not applying a constant supply, DC supply, rather we are applying a variable supply. It is available for this duration, then off for some few duration, that E off represented here, and then again turn on. So, it means that it need to have that provision to turn it on and turn it off at desired instant whenever we want it. And if when see when it is turned on, the current it start rising here, because this voltage is applied across the load through inductor. It is slightly delaying that rise. So, this rise you can see when it is turned off, the energy that is stored here, it is going to dissipate across this load. So, this whatever is stored, it will pass through this, and in the meantime this freewheeling diode will also come to picture. So, that freewheeling diode, once it comes into picture, it short circuits the load. So, once it short circuit the load, that automatically indicates that the voltage across your load will be 0, and during this time whatever energy is stored, that is being dissipated. So, it means that current is going to go down and it is not exhaustfully. In the meantime, you again turn it on. So, it can also go to 0 in case you increase the turn on time. So, this is how your chopper circuit works. You are simply turning on your switch by using some pulse, then voltage is applied, and then you turn it off at some instant, keep this device for off for some time, and then again turn it on. So, you can decide that turn on and turn off time, and what we get is we can get this variable DC supply, and this is the average voltage, DC voltage, that we are getting out of this operation. Now, choppers can be classified into various types. The two basic classification is step up chopper and step down chopper. I told you that choppers can be called as the DC equivalent of your AC transformers. Why? Because in AC transformers we can step up the voltage level, we can step down the voltage level. The same is the case here. We can slightly increase the voltage at the output, or obviously the voltage will be lesser at the output, because if we keep it for some time. So, average voltage is less what we are applying. So, in step up chopper the output voltage is less than the input voltage. It means we are getting higher voltage at the output and here in step down, in step up chopper we get higher voltage, and in step down we get the lesser voltage. That is understood. Now, how does the step down or step up chopper work? This is a typical diagram for a chopper, for step down chopper. We are applying a voltage source where we have this resistive load across this step down chopper. Now, thyristors in this chopper circuit acts as switch. So, whenever this thyristor is on, it is just like a short circuit or 0.7 voltage drop depending upon which material is being used. So, this whole voltage is applied across your resistor. So, you can see here the voltage is available here. So, during when it is on, so whole voltage is applied across this, and when it is turned off, it will not conduct, and this voltage across your resistor, your load will be 0, because there is no current flowing through this. So, there cannot be any voltage drop across your load. We must remember that in chopper or particularly in thyristor, that we do not have any control once it is turned on. It can be turned off only if we apply a reverse voltage across it. So, here that is why this dotted line is given, that it has this provision that it can be turned off at your will whenever you want to turn it off. So, whenever the voltage is available across this, means some current is passing through this. So, that is shown by this figure, and we can find out the average value of the DC supply. There is no supply here. So, we can find out the average of this in over a interval of t, and same is the applicable for the current value. So, we can apply the average value of DC current. So, here we know that the voltage that we are getting, DC voltage, is less than what we are applying. So, it is acting as a step down chopper. Now, if we try to analyze it mathematically, we know if VDC is the average value of the output or load voltage, IDC is the current that is passing through the load, T on is the time interval for the SCR conducts, and T off is the time for which it is off, that is here T on and T off, and the current is IDC, and the voltage across this is assumed as VDC. Total time, that is what we say the frequency time period also. So, it is equal to turn on plus turn off time. So, this is what we say the chopping period, and frequency can be calculated by 1 by T, the simple relationship. Now, how much is the voltage applied across your load, output voltage? That can be calculated by this relationship, that total voltage we are applying multiplied by the time for which your circuit, this is chopper is on, divided by the total time interval. So, this is what we find out average, because if we see a total interval, so the voltage is applied only during T on. So, average can be calculated by this relationship, and this T on plus T off, as you said, is called your chopping period or total time. So, in terms of this T on by T, this is what we say the duty cycle represented by D. So, voltage across your load will be equal to the supply voltage multiplied by the duty cycle. Now, the current can also be calculated in a similar pattern as we calculated for the voltages. So, here we know that it is a resistive load. So, whatever voltage is available there divided by the resistance, you get the average value of the output current. And again, in terms of this duty cycle, because current is also not continuously flowing. Why? Because we have only resistive load, we do not have that RL load. So, if there is inductor, so that current can flow for slightly more time, because current does not allow that change to take place. So, that is why we say that the total current is V by R D. So, how long this current is flowing, on the basis of that we can find out the average value of DC current. Similarly, RMS value can also be calculated. We say that because now the current is also variable in the sense that we have current for some duration, we do not have current for another duration. So, we can find out RMS value, and that can be calculated. We know that this is a standard relationship for the RMS value. So, we can find out the how much is the current passed through that. The second is your step up chopper, means where output voltage will be slightly more than the input voltage. This is a circuit diagram for the step up chopper. Now, here we have two important elements, one is inductor, one is a capacitor. So, these values of these inductors and capacitor, they are decided in such a way that meets your requirement of output voltage and the current. So, if you want a particular voltage level, so you can decide the value of L and C accordingly. Now, here chopper is connected in this way, we connect a load here, there is a diode, we apply some voltage across this. So, whenever we switch on this chopper, we turn it on. So, it means it is conducting, it acting just like a short circuit. So, this V is directly applied across your L. So, it is storing energy during this time, means this is the way the current will flow, and it is storing the energy. And once it is turned off, once it turns off means there is no flow of current, it is storing, it has stored some energy, and once it is this connection is removed, it will try to oppose it. So, polarity get reversed, and this energy stored here will dissipate through the capacitor. Now, it is connected to this. Now, once it is connected to this, so this diode, it gets forward biased, and some voltage will appear across the capacitor as well as across the output, across the load here. We can understand it using this waveforms. So, this is the supply voltage, the fixed voltage you are applying. Then you see when it is on. So, when it is on, it means that it is not conducting, there is no current in this, it is a short circuit across your load. So, the voltage across load at that point of time is 0, and the current through this inductor, this is a source current, it is increasing, but again there is no current across the output also. So, this is 0, and once it is turned off, whatever energy is stored, that is dissipated through this. So, once it is dissipated, so the current is going to decrease, source current will also decrease, at the same time the current across the load will also decrease. But once current is flowing through the load, it means there is some voltage drop across the load, and that voltage will appear here. Same is the case for the next interval. So, it means that we are talking about one cycle where we have turn on plus turn off time. So, in this case, the output voltage that you get, this output voltage will be the voltage, source voltage plus the voltage is stored, that is stored in the inductor. So, that is L di by dt. So, it means the total voltage that we are getting across the output is greater than what we are applying. That is why we say it is a step up chopper. Now, we can find out the output voltage using for this particular chopper. So, we assume that the average inductor current is I, during turn on and turn off time. So, this is the average that we have calculated, we can see it from the waveforms. When chopper is on, the voltage across inductor is V, that is clear. Why? Because this voltage is directly applied across the inductor, because it is short circuited, and the energy stored in the inductor will be whatever is the voltage across inductor, the current through that, and the time for which it is on, because energy is power into time. So, V into I into T, and this is we have taken for the steady state condition. So, that is V I V into I for DC circuits, and T on is the time for which it is on. So, this is the energy that it has stored when thyristor is on, or chopper is on rather I should say. When chopper is off, the energy is supplied by the inductor to the load. I told you that once it is off, so this energy is being supplied to the load. So, here when it is off, the voltage across inductor will be V out minus V L. So, this voltage source is applied plus this is equal to V, that we already have discussed. So, the difference between this and this, we are talking about the voltage across the inductor. So, we can find out the voltage, measure the voltage across output, we know the source voltage. So, voltage across inductor will be output voltage minus the source voltage. So, that is what we have here. So, energy supplied, now that energy is being supplied by the inductor to the load obviously. So, that will be voltage multiplied by the time and into current. So, that becomes your energy. V into I is your power, T is the time for which it is has been off. So, during off time the energy is being supplied back to supplied to the load end. And if we know that let us assume this to be a pure inductor and we neglect the losses. So, in that case energy stored by in the inductor is equal to the energy supplied by the inductor. So, that if you equate those two equations, so we know that the input power is equal to the power stored in the inductor is power supplied by the inductor. So, from here if we solve this, we can find out the output in terms of the T on T of time, because we know the source voltage, we know the time for which it has been on, we know the time for which we have kept it off. So, on the basis of that we can find it out. So, V output will be V T by T minus T on, where T is the chopping period, or we can say your cycle. Now, if we slightly vary this, we divide this by T. So, we get one relationship like this, the equation get modified, V out is V 1 minus this. So, it is in terms of duty cycle, because generally whenever specifications of choppers are given, the duty cycle is that is given. So, we can, if you know the duty cycle, we can simply find it out. So, this is the way we can find out the output voltage, and this duty cycle, if it varies, see if the it can vary from 0 to 1, and the output voltage will also vary. If we put up D is equal to 0, so V output is equal to V. If we put D is equal to 1, so it will become infinity. So, that is why it is less than this. So, within this we can vary it. So, accordingly we can get the variable output voltage. So, simply by varying this duty cycle, or we can find out the what kind of voltage level that we require across the output. Now, we can control the output voltage, DC voltage in chopper. There are two methodologies which are used. The one is pulse width modulation control, or we can also say it's a constant frequency control also, and second is variable frequency control. So, in pulse width modulation, what we do is we keep turn on time varying, and we keep total time T, that is what we say is a cycle equal to some value, fixed value, that is T is constant. So, if you see this from this figure, the output voltage is varied by varying the T on time. So, we have this time T, there are two figures given here, the total time, if you see this total time is T, here it is kept on for this duration only, then in next we can slightly vary it. So, this variation can take place, but variation can take place from this point to this point up to T. So, by varying this, what we are varying? We are varying the width of the pulse or the voltage that we are applying. That is why we say it is pulse width, means width of the pulse is being modulated. That is why the name is pulse width modulation. The second way is using this variable frequency control. So, it depends upon the application where you are using it. So, in this case the frequency can be varied, means if you see this time period, this t here and the t here, it is different, it is more in first case. So, t is being varied, but the turn on time of the chopper is kept constant. So, here we keep this this constant, but frequency is varied, and this method produce some harmonics in the output. And that is, and if you keep this turn of time long enough, so it may also become discontinuous in the sense that if we have RL load, so there can be continuity of the current can flow for some time, because inductor will not allow that change to take place. So, it will elongate that flow of current through this, but if turn of time is very high, so current can die down and ultimately it can become discontinuous. So, sometime in some applications it is required that we need to have discontinuous current, because it can cause problem in the commutation, being commutation means turning off, or in some cases we would like to have the continuous current. So, we can decide this, that what should be the turn of time, but what we have is, in first case we were simply varying the turn on time. In second case we are not varying the turn on time, we are varying simply the total cycle. So, these are two ways with the help of which we can vary or we can control the DC output voltage. Now, how do we evaluate them? The performance parameters on the basis of which we evaluate the chopper, first is the thyristor's performance. It can be thyristor or any other switching device. If we talk particularly, because thyristor is the main device which is used for making chopper, it requires minimum turn on time and turn off time. We say that it is turned on, we get some voltage, if it is kept off for some time. So, it is required that thyristor has some minimum time, that is what we say is latching current and holding current, if you are familiar with the terms. Latching current is the minimum amount of current which thyristor must acquire before it is fully turned on, means thyristor is turned on by applying a simple pulse. But if the current across its anode and cathode is not more than equal to the latching current or greater than that, so even if you apply a pulse, it will turn off. So, it need to have that potential across, that is important. Second, similarly turn off time. What happens if you turn it off and suddenly apply the voltage across that, it can again turn on even if it has not attained latching current. The reason is that during turn off, what happens, the current has to go below the certain value, that is what we say the holding current. In that process also, the electron, the charge carriers which are there, because a semiconductor device, they are still in motion, it means they have some energy, and if we apply a voltage across that again, it can turn on again. So, for proper commutation, because we want to have a variable voltage, we want to make sure that it is turned on at a particular instant. So, it has to follow these requirement of this. If thyristor is performing well, if it is turning on and turning off at a required instant, it is going to perform very well. Similarly, duty cycles can be varied only between a maximum manually. So, it is not like this that we can vary it to infinite value, we cannot get voltage very high. So, D can be varied within certain limits, and accordingly on the basis of that we can also get a particular voltage level. So, it cannot be used raising a voltage level just like in a AC transformer, where we can go to up to some kilovolts kVs, but yes, we can vary slightly to a certain extent. Then is the ripple. The biggest problem with these devices, switching devices, is the introduction of the harmonics, because whenever there is switching takes place, certain components of multiple of fundamental frequency, they get introduced, and as a result of that some ripples may come into the your load current, and that is also again going to cause some problems. So, we need some filtering requirement also. If it is having lesser ripple, so it is going to perform well. Similarly, to reduce these ripples, frequency has to be high. So, these are some parameters on the basis of which your thyristor performance can be evaluated. Now, comes to the classification. The choppers, they are classified on various categories. We have class A, B, C, D and E chopper. Now, there is a reason or basis on the basis why we have classified, and this is simply the nomenclature A, B, C, D E given, but A, B, C, D is given on the basis of where they are working on in a particular quadrant. So, that is why this categorization has been done. There is another classification where we have on the basis of commutation, turning off, how we are turning off your device. So, voltage commutated, load commutated, current commutated choppers are also available. Then there are some special choppers available, Morgan Jones choppers. So, there again they are all again under the category of commutation, but we need to understand the fundamental that the where we want to operate our device, whether we want a voltage, positive current, a negative voltage, positive current, or in which quadrant we want to operate it, that is what is important, and rest can be easily implemented. So, class A chopper, this is a circuit diagram for the class A chopper. Again we say this is the chopper, which is again having that triggering and the commutation components along with this. Now, here we have this load connected to this, a freewheeling diode connected in parallel, anti-parallel to your load. So, when chopper is on, we turn it on. So, this supply voltage is directly applied across this, because this is short circuit. So, this voltage, if you see, this voltage is directly applied across your load. So, it means whatever voltage is here, same voltage is appear across this. So, voltage across this at this point of time is positive. Similarly, the current flow through this, it is also forward. So, we say it is positive current. So, if you see this, the forward current, the forward voltage. So, this is the operation in the first quadrant. And in case when it is turned off, because we want to, we will turn it on and turn it off. When it is off, then what happens? In that case, it depends upon the load. If it is R load, so there is no possibility of any freewheeling operation. But if it is RL load, so that current which is stored in the inductor, that will flow through this. And once it flows, means freewheeling diode, it is getting short circuited, and the voltage across your load will be 0, but the direction of the current, if you see, that remains similar. So, it is forward. So, current is always positive and voltage will either be 0 or it will be positive. That is why we say that class A chopper is a first quadrant chopper, this is the last statement, and the average value of the output voltage and current are always positive. That is how we classify these choppers. Now, class A chopper is a step down chopper in which power flows always from source to the load. That is obvious, it is flowing, there is no way it can flow, because chopper is not going to conduct in reverse direction. Then it is used to control the speed of the motor, yes, because the speed of the motor ultimately it depends upon the voltage, or the flux control can also be done. So, there we can flux is again applied by the DC supply. So, if you can vary the DC, you can get the variable flux, and from variable flux we can get a variable speed. So, that is how this is being used for this purpose, and this is we can find out the equation mathematical analysis can be done for this purpose. This is a single the waveform representation for this, that we are applying a gate pulse, chopper 1 is on. So, in this case the current is increasing through this. Once it is conducting, so the voltage appear across this. So, this is the voltage will appear across this. When it is turned off, so current starts flowing through this. So, this is conducting, so it is short circuiting the load. So, there is no voltage across this. So, that is how this during the freewheeling diode it conducts, there is no voltage, but current is still flowing, and the current is going down. Why? Because the current that is stored in the inductor, it is getting dissipated. So, it is slightly decreasing in nature. Again when we turn it on, again we apply the gate pulse again. So, current starts building up again, the voltage will appear across this. Why? Because that SCR this this voltage source is directly applied across your load. So, this is how we can we can find out the voltages. So, we can find the average value of the voltage here. This is the turn on time, the turn out period is T. Now, the class B chopper. In class B chopper, what we have is this is a circuit diagram for this. The chopper is placed at this position now. In this case, when chopper is on, it means when chopper is on, it cannot conduct through this, because we have a diode here. So, the conduction is possible through this only. So, once it conducts this battery, it will force this current to pass through this, but once it is conducting, it is acting as a short circuit. It means the voltage across the load will be 0. and the direction of the current will be reverse. Why? Because this battery is having high potential at that time, and this current flows in the reverse direction, means it is opposite to what we have taken here the convention. That is why I see the current is in the negative direction. Now, during this on time, when it is off, once it is off here, what happens? Whatever energy during this conduction, the energy is stored in the